Hey everybody, welcome back to Algebra 2 online. So the plan for today is to talk about the graphs of secant and cosecant. And the next video we'll talk about the graphs of tangent and cotangent. To start off, I just want to talk about the reciprocals of certain numbers here, okay? So, certainly a reciprocal of like 1/7, right, would flip around, you'd get 7. 14, 1/14, right? This one, particularly weird, if you do the reciprocal of 0, right, it's going to be undefined, right? We would have like 1/0, and that's not a thing. You can't take something and split it into 0 parts evenly. If you have the reciprocal of a large number, right, it's 1/999 here, so it's actually a really small number. And kind of vice versa, if you flip 1/999, it would become 9999, right? So really small numbers become really large numbers. And these last two are kind of related because reciprocal of 1 is 1, and the reciprocal of -1 is also the same thing, it's -1. So there's actually a reason I picked all of these very strategically here. And if you remember, there's secant and cosecant are the reciprocal trig functions. So secant is 1/cosine, right? And cosecant is 1/sine. And so you're going to see this kind of stuff show up later when we get to graphs, okay? And just to pick out a few points, I got this little table down here, right? If, we have an angle of 0, we can plug that into like sine, we get 0, right? But if we're talking about cosecant, right, whenever sine is 0, then 1/sine for cosecant, right, should be undefined. So one of the things you're going to see is that there's going to be vertical asymptotes for these graphs. This is the exact same reason, like 1/x, this graph right here has the vertical asymptote. So it's just you're doing 1/0, and so you're going to get vertical asymptotes. And here in 1/x, you just get one of them. You get one at 0. But because sine of a whole bunch of different angles is 0, you're going to get a whole bunch of vertical asymptotes, actually infinitely many. But like a lot of the other numbers are fine. Angle of pi/6, 30 degrees. The sine is 1/2. Cosecant then is 2. Pi/4, you get √2/2 for sine. So here you get 2/√2, so on. Another interesting one, though, is, when we plug in pi/2 to sine, we get 1. And the reciprocal of that is just the same thing. It's 1, right? And this would have also happened when we get -1, right? At like 3pi/2, we get -1 for sine. So that is going to be a nice thing, and it's going to actually help us graph these functions. Really roughly speaking, the way that we graph secants or cosecants is that we basically graph a sine or cosine. So let's just say that's like sine of x. And then what we do is we're like, okay, at any of these zeros, right, we're going to get vertical asymptotes because, that first row right there in this table. If sine is 0, 1/sine is going to be undefined. So there's vertical asymptotes periodically throughout the graph. And then we know that like the sine has its max at 1 and its min at -1. But because of the reciprocal of 1 is 1 and the reciprocal of -1 is -1, the cosecant graph will just match up like perfectly at those max and min points. And so what you get is you sort of get this general shape. I keep hitting that over. You get these kind of weird, you saw them in the last video because I had a cosecant actually graphed. But it literally looks like a bunch of disjointed like parabolas in a sense. It looks parabolic because as this sine graph gets smaller and smaller and smaller and smaller, when you take the reciprocal of a smaller and smaller and smaller number, right, think this one, you get bigger and bigger and bigger. And so there's sort of like a they're approaching away from each other as you move towards the asymptotes like that, right? As you get numbers closer to 1, right, it should come in, and then at 1, they should literally touch. There's one point, there that they touch, and then they start to go away from each other again. And that's just due to the behavior of the reciprocal of increasingly smaller numbers, giving you increasingly larger numbers and that kind of thing. So the way we graph it is literally we graph the sine or a cosine, and then we just sort of draw dotted lines where there's zeros, and then connect the little curves with the max and min spots. So I'll go through like a formal example here, but first thing I would do, if I have minus 3 cosecant of 4x, I would want to really graph minus 3 sine of 4x, okay? And once I graph that, this will actually just be super trivial because I'll just like connect it with this certain curve. The way I would graph this, right, same old thing, do the period, 2 pi over b. b is 4, so I get pi over 2 is the period. And so let's say that's pi over 2. This is pi over 4. This is half of that. It's pi over 8. And then again, 1/8, 2/8, 3/8, 3 pi over 8. And then the amplitude is 3, right? And there's no like vertical shift on this graph or shift up or down, right? So the amplitude of, this 3 and this -3 is really what we get. The only other thing that's happening is there's a negative. So normally we would go up and then kind of come down like this, right? That would be sort of the normal graph. But we're going to flip that. Like instead of going up first, we're going to be down here, and then we're going to end up there. So it's going to look like that. So we would get sort of these points as our, kind of our points on thinking like quarters on the unit circle. And I'm going to do this dotted because we're not actually asked to graph, minus 3 sine 4x, but that is what minus 3 sine 4x should be. And the real question was, what is minus 3 cosecant 4x? So all you got to do, the max and min points are shared, okay? The 0 points, whatever really would just be on the midline, so like this would be on the midline, this and this, right? Those are going to be undefined because that's where it would be 0. And then using the dotted lines as kind of barriers, you just make either upside down parabolas like that or right side up parabolas like that. And that's all it is. That would be one full period of minus 3 cosecant 4x. And that would just kind of continue. You'd have another open up parabola here, and then over here you kind of get one that comes down. Here there'd be one that's like down. So the yellow graph with those dotted lines, I do want to see those too, is what I'm looking for. And I just kind of want to highlight some important points over here. So the domain for cosecant is all reals, but when sine, maybe I'll say the corresponding sine function equals 0, right? So here the corresponding sine function is minus 3 sine 4x. When that one equals 0, this graph will be undefined, okay? But every other x value you could plug in, right? The period is no different. You still calculate the period just by doing 2 pi over b. That's still there, okay? And the asymptotes are just where basically the corresponding sine function is 0, right? So wherever this thing was 0 is where you're getting the asymptotes. And you truly get infinitely many of those asymptotes, right? It's just going to continue forever and ever and ever. So let's do a secant, okay? And, as you probably would expect, basically the way to do this is to graph the corresponding, in this case, cosine graph, right? I'm also going to take the pi over 3 out. And so I'm going to actually fill that in here in a second. So I want to just write it this way. I never want to write them that way because I want to see when I have the two things in there, there's definitely a shift right going on. But I want to know exactly how much. It's not actually pi over 2, right? Because there's like a multiplier in there. So I'm taking the multiplier out. And then I really just want to think, okay, pi over 3 times something equals pi over 2, right? And so, the something you can just get by doing pi over 2 divided by pi over 3, right? Just divide that over. And so if you do that out, you'll see that that number in there has to be 3/2, right? So that is my corresponding cosine graph. And that is really what I'm going to graph first. And I'll do it kind of like dotted like this. And then I can get secant from that. And maybe just to highlight here too, secants, okay, are defined also for all reals except when the corresponding, all reals like this, but when the corresponding cosine graph is 0, right? Because 1 over 0 is undefined. And the period is still 2 pi over b. And the asymptotes are when the corresponding cosine graph is 0. Okay? So let's move on to graphing this. Okay? So same kind of place. I always like to start with the period. 2 pi over b. b is pi over 3. Right? And so if you do that out, so you would get, the pi's would cancel, multiplied by 3, so you get a 6, okay? So my period is 6, so I got 6, 3, this is 3/2 then, and so this would be 4.5, which is just like 9/2, right? Okay. So that is the period, like the 4 tick marks from the period marked out. And we see that there's an amplitude of 4, but we do have a shift up 1. And so the midline on this thing is going to be up at 1. Let's just say that's 1 right there. So that's my midline, okay, dictated by this. So if I go 4 above that, I'll get the highest point, and 4 below that, I'll get the lowest point. So 1, 2, 3, 4. 1, 2, 3, 4. Then there's a shift. So normally cosine would be like here, 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 right? You get that kind of shape for cosine. But there's a shift to the right, 3/2, okay? And so basically that's actually kind of nice with this problem because everything just shifts, one kind of unit tick mark over here. And so the point that would have been here is shifted over here. And then the point that would have been here is shifted over here. And so, again, you're going to get that point and that point. And then, there would have been a point here that was shifted off the slide. But I don't really have room for that, but we can bring in, there would have been one over here that would have been brought over to here. So I'm just going to kind of do that as my other point. And so that would be let me label these things. This is 1, 2, 3, 4, 5, right? This should be -3. 1, 2, 3, -3. That would be the 4 cosine pi over 3 times the quantity of x minus 3/2 plus 1. So to get the secant, right, all you got to do, it's actually really quick, wherever there were these zeros, the things on the midline, right, you're going to have vertical asymptotes. Put those in. Then these max and min points would be shared, and then you just draw in like a curve from that, okay? So that is all I'm looking for to graph these things, right? And you can obviously like check any of these on Desmos and things like that, just to, when you work on homework problems with this, just to make sure that you do understand it. But that's how you would graph for secant pi over 3x minus pi over 2, all that stuff plus 1. All right, this is going to be the last example I want to do in this video. So, secant here, a secant graph, and a cosecant graph, they look very similar because sine and cosine look very similar, right? So sometimes when we see a graph like this, we don't really know whether it's a secant or a cosecant. It could be either one. And so we could ask a question like this. We could say, find two equations that are different, but both accurately describe this graph, right? And so we did one of these in the last videos, kind of part 2 there. I ran out of time. I definitely won't run out of time here. But, to do these, you just sort of start trying to break down the important features that you see. So, what I'm doing is I would kind of think, okay, there's like a sine or a cosine function that kind of can touch and match up with this one. If I just take this blue part right here, that looks basically like a sine function, right? With no shifts left or right or anything, because that's kind of nice. And if this is up at 2, I think you're meant to assume that really max value there is 1, and this is -1. So that also means there's no shifts up or down, and no stretches. So it's basically looking like a normal sine. The one difference is you get a full cycle, full period in pi, right? So 2 pi over b equals pi, right? And so if you cross multiply here, right? Pi b equals 2 pi, so b just basically has to be 2, right? So one function that could do this, because basically it's built off of a sine 2x, is not sine 2x, but of course the reciprocal function cosecant 2x. That is going to be one of my answers, right? That could be an equation for this thing right here. That would do it. Another option is just thinking about it, this graph down here, as as a cosine graph shifted like left or right, all right? We know if this is pi, right, this is pi over 2, then this tick mark is pi over 4. And so you can think like the graph was here, but it was shifted to the right, pi over 4, right? Like if I, take something like that, that's kind of what cosine looks like. And so if I took that orange graph and I shifted it, just over to the right, every like important point over to the right, you could get what we have right here, right? If you shifted every point over the right by pi over 4. Sorry, I labeled this. Oh no, I think I just erased too much when I did the erase. It's pi over 4. And so that would do it. So, basically we're just going to build off of the period's still the same and everything. It's just that we're kind of thinking, okay, we're building off of a cosine 2 times x minus pi over 4, because that's like the shift in there. But of course we don't have cosine, right? We have secant of 2 times x minus pi over 4. That is it. So that one or that one, if you go graph it on, Desmos or something, you will literally get this weird graph, just like that. So that's about everything there is to it for graphing secant and cosecant. Next video, we will graph tangent and cotangent.